Hello, this is going to be a quick video explaining partial derivatives. I'm just going to go over the partial derivative with respect to x. Basically the same stuff applies if you do it with respect to y. And so let's start. We have this equation here, uh, f of xy equals x squared plus y squared, and we're going to find the partial derivative at this point, x equals 1, y equals 1, and then f of 1, 1, which is 2. So if you plug in 1, 1 squared is 1, plus 1 squared, 1 plus 1 is 2. So z equals 2. And first, though, we're going to take a look at y equals x squared and just kind of review a little bit what taking the derivative does in this case. So if we have the xy plane and we have this y equals x squared, which is a parabola, and let's pick a point, and we're going to call it 1, 1. So we're going to find the tangent, the slope of the tangent line at this point. And it's going to look something like this. And to find it, we can take the derivative. So the derivative of y equals x squared is y prime equals 2x. So this tells us the slope at any point. And to find the slope at that specific point, you plug in the value. So we're going to plug in 1 for x, and we're going to plug in 1 for y, but there is no y value, so that doesn't even matter. And our slope is going to become m equals 2 times 1, which is 2. And to find the actual equation, we would have y equals mx plus b, and we're going to have the y value is 1. 1 equals 2 times 1, which is 2, plus b. So we see that b equals negative 1. Write that over here. B equals negative 1. And now, from this, we say that y equals 2x plus 1. That gives us the formula for the tangent line, which is this line right here. And if you plug in 0 for x, you'll see that this goes to the point. Oh, sorry, this is supposed to be minus 1. 2x minus 1, because this was negative 1. So this goes to the point 0, negative 1. Now, let's kind of take the same ideas and apply them in this 3D space. So we have this graph. It's going to be x, y, z. And this is going to also have kind of a parabola shape, but it's going to basically look like a bowl, or maybe like a tornado shape. It's like a parabola, but it has 3D, 3D circles all extending upward on the z-axis. And here we're going to consider this point, which was 1, 1, 2. So we go 1 on the x, 1 on the y, 2 on the z. And now we can find some different things from our partial derivative. We can find the slope of a tangent line, or we can find the tangent plane. So if you were to take, let's go ahead and do the partial derivative. So the partial with respect to x of at xy here is going to equal, so to do this, we just take the derivative of anything with an x as normal, but anything with another variable, we treat that variable as a constant. So the derivative of x squared is just 2x, and the derivative of a constant is 0. And this is also going to tell us a slope. So now what we can do with this information is, let's go ahead and get some formulas. So formula that's commonly memorized is 1, 0, partial f with respect to x, and this is the direction of the tangent line to this point. And what I mean by that is, so what this will tell us is if we have a tangent line to this point that's tangent to our surface, but the line is parallel to the x-axis, the direction of this line is found by this vector equation. And if you change this to partial f with respect to y, it would be the same, but it would be parallel to the y-axis. And if you were to find all of the tangent lines here, extending in any different direction, but still tangent to this point on the surface, then that would be the tangent plane. The actual formula, though, what we're going to plug in to use this direction information is we're going to have x0, our starting x value, plus our direction times t. And the same for the y. So y0 plus the direction, which is 0, times t. And then for the z-axis, it's going to be z0 plus partial x, which it's going to get a little bit messy. The partial f with respect to x at x0, y0. This is our direction information, and we have to multiply that by t. So we're going to use that. And let's go ahead and do that. So our starting x value was 1. So this will give us 1 plus t. Our starting y value was also 1. So this is 1 plus 0t. Our starting z value was 2. When we plug in 1, 1 into our function, we get 2. Plus, now the partial of f with respect to x, but plugging in x0 and y0. So this is the partial, and when we plug in 1, we get 2. So 2t. So this is the equation for the tangent line that is parallel to the x-axis. One more useful thing that we can find, and for this one we're going to use the formula z equals z sub 0 plus the partial with respect to x of our starting point, x0, y0, times x minus x0 plus the partial with respect to y of y minus y0. When we plug in all this, this will tell us the tangent plane. So let's do that. Z equals z0 was 2 plus the partial, which we just used over here. It was 2. Partial with respect to x, then plug in x and y, which there's no y value. We'll plug in x, it's 1. 2 times 1 is 2. So we're going to take that 2. I'm going to go ahead and distribute now. We're going to take the 2 and multiply it by the x to get 2x. And we're going to take the 2 and multiply it by our starting x value, which was 1. But this is negative 1. So 2 times negative 1 is negative 2. Then we do the same thing with the partial with respect to y. Oops, I didn't write in the partial with respect to y of x0, y0. It's supposed to be there. So we're going to do the same thing, but I didn't actually do that already, but it's going to be the same because it'll be, this is a constant, so this is 0 plus, and then the partial of this with respect to y is just going to be 2y. And then once again, 2y times 1 will give us 2. 2 times y gives us 2y. Then when we plug in the 1 here, we get negative 1. 2 times negative 1 is negative 2. We can simplify this a little bit because this negative 2 can cancel with this positive 2. So we get z equals 2x plus 2y minus 2. Now this is the equation for the entire tangent plane to that point. And just to illustrate this a little bit better, I'm going to show this using a free online graphing program that I happen to really like. You can see I left the URL up there, so if you feel like using it. So I already put in the surface and the point. So this is the surface, z equals x squared plus y squared. And there you see the point. The point was 1, 1, 2. And now just to show this right here, x equals 1 plus t, y equals 1, z equals 2 plus 2t. That was our first tangent line that we found, which is tangent to the point on the surface, but in the direction of x. You can kind of see better as I rotate that around, what's going on there. So there's that. And then just to show real quick the full tangent plane, this is what the tangent plane looks like. Of course, it's a plane, it extends out in all direction. The shape here has to do with the parameters that I just left them as the default, but you can see that that plane is fully tangent to this surface at that point. The only place it touches that surface is at that one single point. So there you go.